So you are familiar with the concept of complete matrix space. Complete matrix space means if in a matrix space XD, every Cauchy sequence is convergent, then we call it as a complete matrix space. In previous video, we have seen definition as well as one example also. So let us discuss one more example of a complete matrix space. So here they have mentioned R2 with a Euclidean distance D. So we have to prove that it is a complete matrix space. That means simply we have to prove that every Cauchy sequence in R2D is convergent in R2. Okay. So let us start with one Cauchy sequence. Let Zn be a Cauchy sequence in R2. See, basically it is a Cauchy sequence in R2. So obviously it will have two components. So I will mention where Zn is equal to xn comma y. So there will be two components getting. After that, I am assuming let epsilon greater than 0 be given. Let epsilon greater than 0 be given. Okay, so epsilon is so much required for a definition of Cauchy as well as convergent. So I have assumed epsilon greater than 0. So we have Zn is a Cauchy sequence and our target is to prove that it is convergent in R2. Let us use the definition of Cauchy sequence here. So I can write, so therefore for above epsilon, there exists n belongs to set of natural number such that d of Zn comma Zm less than epsilon for all nm greater than or equal to capital N. But see here D is a Euclidean matrix, so that's why we can write in terms of norm also. Okay, so therefore what can I write? This is norm Zn, okay, Zn minus Zm less than epsilon for all nm greater than or equal to capital N. But what is our Zn? Zn is xn comma y. And what is our Zm? It is xm comma y, right? Less than epsilon for all nm greater than or equal to capital N, right? So you know that how to subtract. Obviously, component wise subtraction is here. So therefore, norm xn minus xm comma yn minus ym, right? Less than epsilon for all nm greater than or equal to capital N. So you are familiar with the definition of norm. With the help of square root, we can easily define norm. So yeah, let us use that thing here, definition of norm. By definition of norm, what can we write? Square root of xn minus xm square plus yn minus ym square less than epsilon for all nm greater than or equal to capital N, right? So you know that to remove square root, we need to take square of both sides. Let us do xn minus xm square plus yn minus ym square less than epsilon square, right? See, sum of two non-negative terms is less than epsilon square. That means 100% each of them is less than epsilon square. So this is, I should write here, xn minus xm square less than epsilon square and yn minus ym square less than epsilon square for all nm greater than or equal to capital N, right? So to remove squares, I will take square root of both sides, but obviously I am going to take positive square root. So that's why mod will be there. So implies mod xn minus xm less than epsilon and mod yn minus ym less than epsilon. So you are familiar with this definition. This is definition of Cauchy sequence, right? So therefore xn is a Cauchy sequence as well as yn is also Cauchy sequence, but both are Cauchy in R. Getting? See, actually xn comma yn, this is element of R2, but xn is real number as well as yn is also a real number for a particular R n. Okay, so therefore I can say therefore xn and yn are Cauchy sequence in R. Okay, So r, d I should write du. So usual distance. So these are Cauchy sequence in r du, right? But we know that in previous video we have proved, yes, r with usual distance is a complete metric space. So let us use that thing here. But there is no more space to write. So make a screenshot of it, then we will go further. See, but we know R with a usual distance is a complete matrix space, and we have Xn and Yn. These are Cauchy sequence in R. So therefore, by definition of complete matrix space, Xn and Yn are convergent in R. Okay, so let us write that thing. So therefore, Xn and Yn are convergent in R. Since we know that complete matrix space says every Cauchy sequence is convergent in that matrix space. So here R is complete matrix. So therefore Xn and Yn are Cauchy. So therefore they must be convergent in R. So that's why I could write it. So Xn and Yn are convergent. That means they will converge to some particular point. Getting? So I assume here Xn converges to X and Yn converges to Y. And say Xn converges to X and Yn converges to Y. Okay, both are real numbers, right? So here we can use the definition of convergent sequence. So you know that definition of convergent sequence: for given epsilon greater than 0, there exists n belongs to set of natural number and so and so. So see, epsilon already we have assumed. So let us use that epsilon here. So therefore, for above epsilon greater than 0, there exists n1 comma n2 belongs to set of natural number. I have taken two natural numbers, n1 for this first sequence and n2 for second sequence, such that what can we write? Mod xn minus x less than epsilon for all n greater than or equal to capital N, and mod yn minus y less than epsilon for all n greater than or equal to capital N2. I will call it as a star, and this is double star, right? See, a small adjustment I am going to do here. Instead of epsilon, I am going to take epsilon by root 2 and here epsilon by root 2. See, star is true for n1, double star is true for n2, but both of them should true simultaneously. So I am going to choose maximum of n1 and n2. So let n is equal to maximum of n1 and n2. So star and double star will be true simultaneously. So therefore n will work for both star and double star. See, now what will I do? So I am going to consider let z is equal to one point I am considering whose x coordinate is x and y coordinate is y. That means here we have a limits of these two sequences. Now with the help of them, I am going to define one element of R2, that is z, which is obviously element of R2, right? So see, my target is to prove that our original sequence Zn converges to this point Z. So let us do that. Okay. So for n greater than or equal to capital N, consider, I am going to consider T of Zn comma Z. I am going to prove that this is less than epsilon, then we can say Zn converges to Z. So D is a Euclidean distance, so norm Zn minus Z, right? So norm, what is Zn? Xn comma y, Z is x comma y, right? You know well how to subtract, component wise subtraction, xn minus x, yn minus y. You are familiar with definition of norm. Square root, what can we write? Square root of square of first xn minus x square plus yn minus y square. See, here already we have written, so mod of xn minus x less than epsilon by root 2. So let us write that thing. This is less than square root of, its square will be epsilon square by 2, correct? Here mod yn minus y less than epsilon by root 2, but we are taking square, so its square will be epsilon square by 2. So epsilon square by 2 plus epsilon square by 2, we will have square root of epsilon square, square root cancel, we will have epsilon. Getting? So therefore D of Zn comma Z less than epsilon for all n greater than or equal to capital N. So therefore we can say by definition of convergent sequence, we get here, so therefore the sequence Zn converges to Z. Let me write that thing, make a screenshot of it first. See, in this way we proved Zn is a convergent sequence and converges to Z in R2. But Zn is any arbitrary sequence in R2 getting, so therefore we can say every Cauchy sequence in R2 is convergent in R2. So that's why we can declare R2D is a complete matrix space. Okay, we'll stop. Thank you. Bye bye.